the young engineers of today. Sorry about the technical difficulties there. I'm glad at least you guys were able to get signed up for the class. No, Liam, I'm not going to do that. Um, but yeah, I'm glad that that at least you're able to join. As the class goes on, we'll probably get a few more people filtering through. Otherwise, well, I'm recording this, and so that's part of the reason why I'm doing it. But yeah, we're going to continue with OpenRocket. We're going to continue building our uh, model rocket design, and we're going to make it better, and it's going to be more capable and interesting. Well, capable, at least, and be able to go higher and stuff like that. We'll be able to mess around with the values and see what a launch should look like and all that good stuff. So yeah, that's what we're going to spend today doing. Maybe Wednesday as well. Maybe we'll get back to regularly scheduled classes. And by regularly scheduled classes, I mean the other Rocketry presentations that we were doing week before last. Remains to be seen. I guess it really depends upon how much we get through today and Wednesday. But yeah, so let's go ahead and get OpenRocket opened. That'll take a sec. Oh, it's going to happen so much faster too. Double the amount of RAM that's on my computer. So let's see here. Yes, this is the one that we were working on not last week, but a week before that. Let's say well, at least it arrived. Yeah, that is annoying. But I'm glad that it arrived at least. And hopefully, presumably, it's fully functioning and working so that you can actually get your computer built. So yeah, this is what we're looking at. This is the rocket that we built last time around, and we actually finished off with the motor configuration. So we went ahead and we made a nose cone, and we went through all the different sort of options for that. The shape parameter, defining the shape of the nose cone, the length of the nose cone, the diameter of the nose cone, the thickness of the nose cone wall, that is to say the inside of the nose cone. So there is some open space inside of the nose cone since we only have a wall thickness of 0.2 centimeters and its diameter is 2.5. So if you were to do the math about the widest part of the nose cone, whoa. All right then. If you were to do the math about the widest part of the nose cone, we shave off almost half a centimeter, so there is a diameter of 2.1 centimeters on the inside that is just open air. Made it out of polystyrene. We customized its color and everything like that, and then gave it a shoulder, which is this basically the plug right here that plugs into the think of like a wine cork or something like that plugs into the body tube in order to keep the nose cone attached until we don't want it to be attached anymore. And that has a diameter of 2.3 centimeters and a length of 2 centimeters. So, there's that. The reason why it has diameter of 2.3 and or a diameter of 2.3 centimeters is because the outer diameter of the body tube is 2.5, but it has a wall thickness of 0.1, which means that the inner diameter has 2.3 centimeters. So it should fit snugly inside of the body tube. We also obviously added the body tube, went over the different parameters of the body tube, and gave it its own custom appearance and everything like that. Made a very pretty looking rocket. Added some fins. Oops. Added 3 fins, in fact. We went over all the different parameters for the fins. That is to say, the rotation of the fins, where they're placed on the body, the cant, if they sort of have like a rifled kind of quality to them. Your application is missing. That's not good. I know those feeling. I know that feeling when your fingers don't exactly work properly. Did you do like a computer-wide search for it? Yeah, give that a try. If not, I guess you'll have to re-download it, which is unfortunate. Yeah, yeah, but it does. It can take a while. Uh, the root chord and the tip chord refer to the length of the fin at different parts. So the root chord is closer to the body tube, and the tip chord is closer to the end. Height is, I believe, yeah, it's the length of the fin. Sweep length is the length of this sweep right here. The sweep angle is the angle of the sweep. Pretty self-explanatory. We got the position, the relative position, which is just where they're placed relative, as you can see here, to the bottom of the parent component, the top, middle, and the tip of the nose cone. We're having it to the bottom of the parent component, so it's just the nose or the fins stop right at the body tube, so they don't hang over or anything like that, even though it kind of looks like it there. Then the cross section has to do with looking at the fin edge on, so like this area right here, that dark and shaded area. We made sure that it was a rounded cross section and it had a thickness of 0.2 centimeters. You know, nothing crazy there, but gives us an idea of, you know, the size of the fins and everything like that, the dimensions. Then finally, we added an inner tube, which is the motor mount. And that was the thing that we were most interested in at the time, is we wanted to make sure that it was where a valid place to put the motor on our rocket, because you need one of those. You need at least one of those. You need one of those for each motor you're going to be placing into the rocket. So this inner tube is a motor mount, which means that that's where the motor goes. Motor overhang, we made it so that the motor hangs out 0.3 centimeters beyond the inner tube. And we also made sure that the inner tube itself hangs out half of a centimeter beyond the back of the body tube. And we just sort of stacked these overhangs so that the motor is easily insertable and removable, because that's probably about as much as we're going to be able to get the motor in with like the motor mount and everything like that. And also just so that the exhaust of the motor, the backfire, doesn't damage like the fins or the body tube of the rocket, because that's definitely going to reduce the lifetime of the rocket. It's going to make it harder for the rocket to be able to, what's the word I'm looking for? Be reusable. And that was basically all of our rocket construction thus far. Now we added a motor in the motors and configuration tab. See up here, so you can see motor mounts. All the possible motor mounts are listed here. The body tube is a possible motor mount, and our inner tube is a possible motor mount. But only our inner tube is a motor mount, so as you can see, it's checked here. If we wanted to, we could check body tube and make body tube also a possible motor mount, but we don't really want to. Just because we've already got the inner tube and we've already, you know, we're already mounting the motor in there. That just seems superfluous. So as you can see here, inner tube is a valid motor mount, and it's listing the motor that is mounted in our motor mounts. In this case, it's an A83. Now, just as a, I guess as a quick review, what does the A represent? Yeah, in essence, it's the size of the motor. How much more or less powerful is an A motor versus a B motor? A is less powerful. That's definitely true. How much though? Oh, no worries. Thankfully, it's pretty easy. A comparable Class B motor, that is to say like a B83 versus an A83, will be twice as powerful. So Class B motors are twice as powerful as Class A. Class C are twice as powerful as Class B, which makes them 4 times as powerful as Class A. Class D, twice as powerful as C, 4 times as powerful as B, 8 times as powerful as A. You get the idea. It's just each letter is double the power. Yeah, so, just a uh, nice easy thing to remember. How about that first number, in this case, the 8? What does the 8 represent? What about the average thrust? Do you guys remember what that is? Or average impulse, I suppose. Well, the number describes basically how... Oh, it's totally gone. All right. Sorry about that, Noah. Don't know what that's about. Let me go ahead and pull up the download link again. Yeah, definitely. There you go. How much thrust it has is kind of, yeah. So like, no worries, Noah. Average thrust is basically how long the rocket burns versus how much energy it puts out while it's burning. So while a Class A rocket only puts out like a certain amount of energy over its entire lifetime, and a Class B engine puts out twice that amount of energy over its entire lifetime, it can expend more energy in a given second, but also burn faster. So think of like a candle with a brighter flame versus a candle with a dimmer flame. Um, the candle with the brighter flame is going to burn out more quickly, but its flame is going to be brighter that entire time. So the same basic principle here. The higher the number, the more energy the rocket will put out in any given second. However, the faster it will burn out. 8 is, I mean, it's all right. I mean, it's not like particularly one direction or another. Um, they can go up to 12 and down to 4 and stuff like that. So it's all fairly relative anyway. Um, so yeah, uh, that's what that number refers to. It's known as like the average thrust or the average impulse. How about that second number, the 3 after the dash? Who remembers what that represents? How about the ejection charge time? Yeah, you got it. Um, so that's basically how long it is until the ejection charge blows, measured in seconds. So an A8-3 in this case, after it's expended all of its fuel, it will coast for 3 seconds. The delayed charge lasts 3 seconds until the ejection charge goes off, and then the parachute or whatever recovery system they have blows. So if you have like an A8-5, the delay charge will be 5 seconds. 4 seconds, 2 seconds, 6 seconds. You get the idea. Um, So yeah, you've got the basically the total power, the average power, and the delay charge length. That's what those three different things represent. So in this case, A83 is kind of a middle of the road, pretty weak engine, nothing crazy. And the rocket will coast for 3 seconds after it runs out of fuel before the ejection charge blows, and then the recovery system deploys. And the recovery system, in this case, we're probably going to make it be a parachute, but it could be streamers, it could be that nose blow one, it could be, you know, it could be a it blows the ejection charge downwards at the last possible moment. I mean, you know, there are a number of options. So let's continue with building our racket. So we made our A83 engine. Let's do a few more of them. And this will be a good way to review how to look at the motor configuration window as well. So I'm going to go ahead and create a new configuration. And as you can see, another configuration popped up down here that said no motors. In fact, I'm going to click it 3 more times. So we'll have 4 blank configurations. And I'll just double click on the first one. And again, we've got all of our Estes rockets here because I over here in the filter system, I made sure that Estes was the only one that was checked, or Estes. So we've got all of our Estes engines listed. I gave it so that the total impulse, we could look at all the engines. If we wanted to, we could slap a G-class engine in here. As you can see, the shaded part is the actual motor, so it does not fit in our rocket at all, although it likes to pretend that it does. So, you know, we'll see that our max acceleration is 602 meters a second, and it'll reach a height of 1,641 meters. But that's not what we're interested in. What we're interested in is a B4. I know, it's boring. So a B4 and then an ejection charge delay of 4, which is actually what we want. So we'll go ahead and hit OK. As you can see, the engine is slotted in there. Whoops. And we can also see that, you know, it'll reach a height of 174 meters and a max velocity of 66 meters a second, which is almost 1/5 the speed of sound, almost, which is pretty fast, and a max acceleration of 216 meters a second. Certainly faster than our Class A engine, and more powerful. Look at this apogee of 73.2 meters. On the B4, it goes all the way up to 174, so it's more than double. Speed is almost double. Its acceleration is what, like 1 1/3, sort of. Oh yeah, right. Okay, so the thing is, you set up the ejection charge delay afterwards. So if you select B4, you can manually put in an ejection charge delay in this text box here. So you just click on it once in order to get it, and then you put in the ejection charge delay, hit OK, and boom, there you go. So now we've got our A83, our B44. Let's see what else we got here. A C63, so I'm going to go ahead and click on C6 once. The ejection charge delay is 3. That's great. We're going to go ahead and hit OK. So now our C63 is added. We'll do the same thing here. We'll make it a C65 instead. So now we got a C65. And then finally, we're going to add a C67. Bam. Boop. All right, so now we've got 5 different motors. A83, B44, C63, C65, and C67. And based on what we went over, you can see that these last 3 motors are actually the same class and average thrust. It's just we're fiddling with how long the delay charge lasts until it goes. So in each of these, literally the only difference is how long we're letting the rocket coast before the recovery system deploys. And in fact, if we look at the calculations down here, the apogee is the same in all of them. The max velocity is the same in all of them. And the max acceleration is the same in all of them. Now that remains to be seen. This is, you know, sort of a based on the mass of the rocket and the power of the engine, this is sort of a preliminary kind of look at everything. Although we might see some different behavior once we actually start simulating the flights, because this doesn't necessarily take into account, um, you know, whether or not the rocket is still coasting upwards when the ejection charge blows. So that might mess with our apogee, things like that. We'll see that in clear detail once we actually simulate the flights. Now, here's the other thing. You notice that we've got our two circles here. Does anyone remember what these circles are? Yeah, well, close. Not the center of thrust, but the center of pressure. But otherwise, yeah, definitely it's the center of gravity and the center of pressure. Um, Excellent. Glad to hear it, Noah. Hopefully it should just run first go like nothing. Um, so yeah, we've got our center of gravity. It isn't with your files? Oh, like in your downloads folder? What browser did you use to download it? Okay. So when you download something on Chrome, it should appear in the little toolbar down here. If you click on the arrow next to it, there's an option for show files in folder, and you should be able to find where it's deposited on your computer, because it should just take you straight to it. Okay, so if you go up to the three dots in the upper corner, you can go to your downloads um, downloads window. And it should list all of the downloads that you've done over the since you last cleared your history. And then from there, you'll be able to select show in folder. Awesome, for sure. Okay, so center of gravity and center of pressure. Center of gravity is where where all of the mass on the rocket is centered. So that's where you find like an even weight distribution on either side. As a side note, the center of gravity is also generally what follows the arc if you throw something. The flight arc of something that you've thrown, I should say. The rest of the object will rotate around the center of gravity. Again, assuming all things equal. Now, there are other things like wind resistance and stuff like that that can mess with that. Enter the center of pressure. The center of pressure is basically where an object will rotate around when it's acted upon by forces like drag and stuff like that. So as drag is redirecting the rocket through its fins and its nose cone and everything like that, it'll rotate about the center of pressure, which brings us to stability. Stability is a measure of, well, how stable our rocket is. A stability that's too low means our rocket will be unstable, and a stability that's too high will mean that our rocket is also unstable. We're aiming for a stability within a certain range. Does anybody remember what that range might be? Well, let's back up a little bit. The stability is measured in calibers. Does anybody remember what a caliber is? I mean, it's all right if like none of this stuff is really ringing a bell. It's been a while since we've covered this material, so if it doesn't come to you, like, Don't sweat it. I'll give you a hint as to what a caliber is. All right, so a caliber, all a caliber is the diameter of the rocket at its widest point. That is a single caliber, and we want our stability, that is to say, our distance between the center of gravity and the center of pressure, which should always be behind the center of gravity, to be between 1 and 2 calibers. So as you can see here, our stability is 1.75 calibers, and our center of pressure is definitely behind our center of gravity. So this rocket's probably going to be pretty stable. Whoops. As you can see, all of these motors are the same size, so we're not really getting any difference in stability. However, as I go to smaller motors, since the motors weigh less, more of the weight is evenly distributed between the nose cone and the motors and everything on the back, so the center of gravity moves forward. See, if I go click back on C, you can see that the center of gravity just kind of pops back a little bit. B, it's a little bit forward, and A, it's a little bit more forward than that. And our stability measurement changes. B is right on the edge of stable. Like, we might still be able to get away with that, but we could certainly improve upon it. A, we probably don't want to fly a rocket like that. 2.25 calibers is a little bit too far unstable. Again, not exactly, it's still kind of close, and it's going to be on a case-by-case basis. Some rockets you'll want the stability to be a little bit different range, but in general you want it to be about 1 to 2 calibers. So looking at these two, these aren't, strictly speaking, ideal solutions. This C-class rocket engines actually provide a good amount of stability for our rockets because they put enough weight in the back of the rocket that it actually increases the stability. So yeah. Now, yeah, hopefully, oh, okay. We have to add one more thing. We have to add an engine block component, which just stops, as you can see here, stops the motor from moving forwards in the motor tube. So let's go ahead and select our inner tube and add an engine block. Now the engine block is going to be made out of cardboard. The outer diameter is going to be 1.8, but the inner diameter is going to be 1.2 centimeters. Hit enter, and it automatically changes the wall thickness to 0.3. Remember what I was saying before about how there are a lot of triplets of dimensions? So like outer diameter, inner diameter, and wall thickness, these are all related to one another. The inner diameter is determined by the outer diameter minus the wall thickness times 2, because both sides. So in cases like these, you can mess around with 2 of them, and then the third one is going to automatically update so that it makes sense, physically speaking. You can't have, an outer diameter of 1.8, an inner diameter of 1.2, and a wall thickness of 0.1, because that means that your inner diameter and outer diameter are sort of floating apart from one another and not connected, and that doesn't really make any sense in the real world. That's like saying you have a house. Well, it's you run into like a almost kind of like a, who here knows Doctor Who? Show of hands. Okay, a couple people. You run into kind of a TARDIS situation where the inside dimensions don't make any sense with the outside dimensions. It's bigger on the inside. You know, like you have a house that's, what, 50 feet by 50 feet, and um, you walk inside and you measure the floors, and the walls are, and the floors are 48 feet by 48 feet. Well, you got very thick walls, first of all, but you should know that those walls have to be a foot thick, because you're measuring what, like on one side of the walls to the other. If you find through some sort of weird, quirk that the walls are 5 feet thick, that's not going to make any sense. Like, you can't have a house that's 50 by 50 feet on the outside and 48 by 48 on the inside with walls that are 5 feet thick, because it just doesn't really add up. But anyway, so we got an outer diameter of 1.8, an inner diameter of 1.2, wall thickness is 0.3. We're going to change the position, so it's going to be relative to the top of the component plus 0.2 centimeters. And you should see like this little thing just sort of appear there. That is our motor mount. This is going to be here in order to basically make sure that the motor doesn't just sort of fly, this way, and the rocket doesn't fly, because this kills the rocket. Boom. So that's what our rocket should look like. Now you'll notice we don't have any recovery material or anything like that. We'll get there. But for now, we're gonna add a few more things. We're gonna add some centering rings first, and then we're gonna add a launch recovery system, which includes a shock cord, a parachute, and wadding, and then a launch lug, and then we'll have a finished rocket, which we could then run some simulations on. But let's go ahead and add some centering rings. Now, centering rings are used to stabilize the inner tube within the body tube of the rocket. Basically, they'll go, in essence, like right here and right here, or something like that. And they'll always have the same outer diameter as the body tube of the rocket and the same inner diameter as this inner tube. Always, always, always. So if the inner tube size changes, the inner diameter of the centering rings will change. Well, it's supposed to be at the front of the inner tube, which is at the bottom of the rocket, at the back of the rocket. Notice how I have the position relative to the top of the parent component, and the parent component is the inner tube. So make sure that, like, oh yeah. That's definitely, yeah. That should because if you have it at the bottom of the parent component, then actually it doesn't really change anything. Oh, because it updates itself automatically. If I do the bottom of the parent component plus 0.2 centimeters, then yeah, it's going to be floating down here. But let's put it top. Boom. There we go. Oh, right. The inner diameter of the centering rings are always going to have the same diameter as the outer diameter of the inner tube. Oh, man, that's really confusing to say. Basically, you can think of centering rings as mounts for the inner tube. As the inner tube gets smaller, the computer automatically updates it so that the centering rings are thicker, so that the inner tube will always be sort of snugly held by the centering rings. In real life, we would have to put in, if we had a smaller inner tube, we would have to put in larger or thicker centering rings so that that inner tube would be securely mounted. If we put in a larger inner tube, we'd have to put in thinner centering rings so that that inner tube will, not only fit in there, but also be securely mounted. So that's something that this is doing automatically in order to simplify things for us. But basically, the entire point of the centering rings is to keep the inner tube securely mounted to the body tube. So we're going to make sure that the body tube is highlighted, and we're going to select the centering ring in the new component pane. I'm going to select body tube, and over here you can see centering ring, and it's going to automatically give us dimensions. So an outer diameter of 2.3 centimeters, which is the same size as the inside of the body tube, and an inner diameter of 1.9 centimeters, which is the same size as the outside of the inner tube. and a thickness of 0.2 centimeters. So I'm going to go ahead and click close, and I actually, there were a couple of things I needed to do before that, so let me go ahead and select this thing again. But there's one centering ring right there. We're going to add a second centering ring, so that was totally fine. So there, and then we're going to add a second centering ring, and we're going to do negative 4.5 centimeters relative to the bottom of the parent components. Is your engine block a child of the inner tube? As you can see here, I've got it. Okay. And your position is relative to the top of the parent component, yes? All right, and what does it say, plus 0.2 centimeters? Change it to plus 0.2 centimeters. When you change it from top to bottom or vice versa, it will automatically change what's in here so that it keeps the same position. So notice how if I go to bottom of the parent component, I get plus negative 6.8 centimeters because it wants to keep it in the same spot. So if you move it to the top of the parent component, you have to update if you actually want it to move. Yeah. So, okay, so yeah, I added two centering rings. One of them, so the outer diameter is 2.3 centimeters. Yep. The inner diameter is 1.9. The thickness is 0.2. The position relative to the bottom of the parent component is plus 0 centimeters. So it should be deposited right here, and as you can see, it is. We got this big old purple rectangle right here. I say big old, but it's not really. It's just that's our first centering ring, which is perfect. So we're going to hit close, so it's right there, and then we're going to add a second centering ring to the body tube, which is going to have the same dimensions, except its position relative to the parent to the bottom of the parent component is going to be negative 4.5 centimeters, which is going to deposit that one right there. So now we've got two. I should really use a color other than blue. Let's use red. So now the one circled with the blue and the red is the one that is plus negative 4.5 centimeters from the bottom of the parent component. The one circled with the black is 0 centimeters relative to the parent component. And those are going to be our two centering rings. It's possible you can get away with one, but two will greatly increase the stability and not be too much weight. As you can see, our stability is gradually getting lower, which is good because when we add recovery stuff like recovery wadding and a parachute and stuff like that, that weight's going to be up in this area according to the rocket simulation, which is going to make our stability climb back up again. So we kind of want to put stuff in here like the engine or the motor block, engine block, whatever you want to call it, and the centering rings in order to sort of put more mass in the backside of the rocket, which is going to make our stability go a little bit more down. And we're going to basically it's a balancing act. We want to make sure that we don't have too much weight on one side or the other of the rocket. So there we go. We've got our centering rings in there. Now it's time to add a recovery system. Now remember that it's pretty important how we organize our parts up here in the upper left-hand corner. So like the the fins have to be connected to the body tube, so they have to be a child of the body tube. The inner tube has to be inside of the body tube, so it has to be a child of the body tube. The engine block has to be inside of the inner tube, so it has to be a child of the inner tube. You get the idea. Now, if we're going to add a recovery system, that is to say like a parachute and some recovery wadding and a shock cord, what do you think we're going to make it a child of? Um, Almost. See, here's the thing. Really only the shock cord is going to be attached to the nose cone. It's also going to be attached to the body tube, though, so we can create a common denominator with all three of them. Yes, sir. Everything's going to be attached to the body tube. Everything's going to be a child of the body tube. So our parachute is going to be attached to the body tube. Our recovery wadding is going to be inside of the body tube. And our shock cord, well, it is going to be attached to the nose cone, is also going to be attached to the body tube. So given the fact that we have a common denominator with all those three, the body tube, we're going to make all three of them children of the body tube. So let's go ahead and click on the body tube. And then we're going to add a shock cord. Boop. Bam. It's going to bring up this this window here. So the shock cord length, we've got the shock cord material, we've got the position relative to, like we always do, the packed length and the packed diameter. So we're going to change a couple of things. So the position relative to the top of the parent component is going to be plus 2 centimeters, which is going to move it back beyond this shoulder, the plug. So it'll start right here, past the plug. Then our packed length is going to be 5.2 centimeters. So basically, if we watch this dotted sort of area right here, when I click away from it, it makes it longer. So we're telling OpenRocket basically how much space inside of the body tube the shock cord is going to take up when it's packed. And its packed diameter is going to be 1.2 centimeters. So now it's thinner. So that is roughly the area that the shock cord is going to take up when it's packed inside of the rocket. Now, obviously, real life doesn't work out like that so cleanly. It's probably going to look like a mess in there. But for the purposes of weight distribution and stuff like that, as you can see, our caliber just moved up a little bit because of that. That's not a bad idea to just sort of fiddle around with that until you get something that makes sense. Our shock cord length is going to be 40 centimeters. We'll just keep it at that. And our shock cord material is going to be elastic. We're going to just keep it at that as well. So we'll get close. So now we've got our shock cord in there. Let's go ahead and add a parachute. So I'm going to click on body tube again, and I'm going to click on parachute. Top of the para component, it's going to be plus 3.2 centimeters. So it's going to float a little bit in the middle of the shock cord, or actually exactly in the middle of the shock cord. But again, we want it beyond the shoulder, the plug on the nose cone, because it can't occupy the same space as the plug, right? Because the plug is pretty much exactly the size of the diameter of the inside of the body tube. So we want to make sure it's beyond that. The shock cord is touching it because the shock cord is connected to the nose cone, right? And our assumption here, the shock cord is connected to the nose cone, and then it's also connected to the side of the body tube. I don't know, like maybe right here? Whatever the case may be. Parachute, not so much. It's going to be attached to the inside, but it's not going to be attached to the nose cone, so we have it floating a little bit away from the nose cone. The packed length is going to be 4.2 centimeters. So we'll see that the parachute gets larger. And the packed diameter is going to be 1.8 centimeters. 1.8. So it's a little bit thinner than the diameter. Our stability has gotten a little out of control, but we'll see what we can do to, maybe it'll still work. So then we're going to add in some recovery wadding as well. So wadding is a mass component and isn't directly specified in the add new component pane. So this is going to be kind of a weird thing. So if we click on body tube, look for the recovery wadding button here under add new component, and raise your hand once you found it. I'll save you some time. It's actually not there. This is not something that is explicitly simulated in OpenRocket, but recovery wadding, regardless of what it does, it's going to have a weight, right? It's always going to have a it's going to have a mass. Excuse me. It's always going to have a mass because we haven't yet invented anything that has no mass whatsoever. That just doesn't, other than maybe like ideas, if we're speaking in a physics sense. So this mass component here, this is what we're going to use in order to simulate a recovery wadding. And it works out perfectly because we know a recovery wadding is going to have a mass, and based on where it's placed, it's actually going to move the center of gravity on our rocket anyway. So it accomplishes two things. We can simulate having the recovery wadding in there, and also we can account for its mass in our rocket. Now, the mass component is just a nice little catch-all thing that can be used for anything that you might have in your rocket that isn't explicitly simulated or simulatable. So like if you have like a GPS component inside of your rocket, or an altimeter or something like that. So you could send data back to a smartphone or something like that as the rocket is flying higher into the air. That's not going to be simulated here in OpenRocket. However, it is going to have a mass, so you can use a mass component in order to signify that. If you stuck like a little plastic army dude in there and attached a parachute to him as well, so he'd come floating down, after the rocket blew its ejection charge. There's no plastic army man component button here, but it is going to have a mass. It is going to mess with how the rocket works. So you can add a mass component to simulate the army man. So I'm going to click on mass component here. And there's since this is just a regular sort of generic thing representing anything that can have mass inside of your rocket, it's got this very creative name, unspecified configuration. Component name is unspecified. We'll go ahead and change that to recovery wadding. And we'll click down here. So as you can see, the name is updated over here to recovery wadding. We got to give it some mass, approximate density, a length, and a diameter. Again, we'll give it a mass and a size. It will figure out the approximate density on its own. So we can mess with 3 of these things, and the 4th thing will automatically be updated. So remember the same thing before? We had three parameters, and we could mess around with 2 of them, and the 3rd would be automatically updated. Well, here we have 4, and we can mess around with 3 of them, and the 4th will be automatically updated. And then we also have to give the position relative to some part of the component. So we're going to make its mass 2 grams. It's going to weigh 2 grams. Enter. As you can see, it moves the center of gravity. The approximate density is 0.16. Bam. Ugh. All right, we'll mess around with the length and diameter. So the length is 3.0 centimeters, and the diameter is 2.3 centimeters. So now we've got an approximate density of 0.16 grams per centimeter cubed, which again was automatically updated. Perfect, that's exactly what we want. And the position relative to the top of the parent component is going to be plus 8 centimeters, so it's going to move way, way back. And we're going to change, obviously we changed the component name to recovery wadding. So it's something that makes sense. We don't have to give it a name. It'll still work just fine, but the name is helpful for us. Because let's say you have an army man, recovery wadding, an altimeter, a little transmitter so that I can send that altimeter information to a cell phone. A who knows, a little LED sign with a parachute attached to it that gets deployed, and as it's floating down, it has a message on it, like a little tiny one or something like that. Whatever the idea may be. Maybe you have all of these things inside of your rocket at once. Well, you're going to have a whole bunch of mass components, and if you don't name them, and they're all just called unspecified, you're going to be like, okay, which one is this one? Which one is this one? Is this one the Army Man, or is this one the LED sign? That kind of a thing. So giving it a name is helpful for us as people, so we know exactly what it is, because again, it doesn't have like a little helpful icon like the rest of the components do, and an already determined name. So recovery wadding, perfect. Hit close, there's a recovery wadding right there. Now you'll notice our stability is 2.42 calibers, still not great. Better than Class A or Class B motors. Our Class A motor is almost at 3 calibers, and our Class B motor is at like 2.2 3/4 calibers. So, not ideal, but who knows? Yes, forgot about the launch lug. Almost forgot about the launch lug. So we're going to actually add a launch lug. And again, because the launch lug is going to be attached to the body tube, we're going to make it a child of the body tube. So I'm going to go ahead and click on launch lug. Boop. We're going to make the length of the launch lug 3.5 centimeters. Hit enter. That makes it longer. The outer diameter is going to be 0.7 centimeters. And the inner diameter is going to be 0.5. Perfect, which means the thickness is 0.1. The radial position is 19 degrees. So it's, not perfectly in line with one of the fins, because that would make it really hard for your rocket if you had a launch lug on exactly the same part of your rocket as the fin, because then the launch rail would have to go through a fin in order to be socketed into the launch lug. Now our stability is 2.42. If we wanted to, we could move this back. Oh. It doesn't really have a whole lot of weight though, so there's not much we can do with the launch lug in order to make it, more stable. So we'll just keep it at plus 0 centimeters, so it's right there. And we'll make it add up. Let's see. Polystyrene. Sure. Why not? Again, still doesn't really change a whole lot, so we'll hit close. So now that we've done this, our rocket is completely done. And it'll be ready to run some simulations on a Wednesday. I know, how disappointing. We were almost there, and we didn't even get to simulations today. But at any rate, this is our completed rocket. So at least we got through all of that today. But I am going to call it a class here. I'm going to go ahead and do the poll questions, and then we'll leave it open for question and answer time very shortly, and then we'll break for the next couple of days.